Hello. Can you hear me? Great. So, we meet again. We seem to be meeting a lot recently. From last time, a correction. In a note, I said, okay to divide by 0. That's obviously not true. I meant okay to divide by x. So you can see that's corrected in the notes from last time. Okay, starting with a question from the WeChat group. Could there be infinitely many deltas? This was a question from Lee or Leah. Yes. If they exist, there are always infinitely many. So let's recall the first example we did. We proved that the limit of 5x minus 3, so let's say that's fx, as x goes to 1 is 2. So we now know how to calculate this from the limit laws. But, if we didn't, it's a good test for the precise definition of a limit. So we want to show that for each epsilon greater than 0, there exists delta such that this is true. And we showed in the example, if you look back, that we can take delta equals epsilon over 5. Okay. So that was the example. And so there are an infinite number of deltas in two sense, because firstly, for each epsilon, we get a delta. So there's of course infinitely many possibilities here. But also recall that we can take delta equals epsilon over 5, but we can also choose any delta in this range. And so that also gives us infinitely many possibilities for delta. So good question, and the answer is yes. Okay, so last time we talked about more sorts of limits and how limits give asymptotes. So let's give one more example of that. And as a reminder of a few things, so there was a trigonometric function sec x, and this was defined to be 1 over cos x. Okay, so let's look at the graph of that. So it has these vertical asymptotes. Oh, do this. Yeah, like that. And let's look, for instance, at pi over 2. So at pi over 2, we know the graph of cos x so the graph of cos x looks like this, starts at 1 and drops to 0 at pi over 2. And well, as it goes past pi over 2, let's write that there, as it goes past pi over 2, it becomes more negative. So you can see from that why the graph of sec x looks like it does, because as we approach pi over 2 from the left, cos x approaches 0 in positive values, so it approaches infinity on the sec x graph. So, in other words, the limit as x approaches pi over 2 from the left of sec x is positive infinity. And the limit as x approaches pi over 2 from the right, well, here cos x is negative and it's getting closer and closer to 0. So sec x is getting bigger and bigger in a negative sense. So the limit of sec x is minus infinity. Okay, so now let's do one last example from this section, and then we'll continue on to a new topic. So, dominant terms. So these can be helpful for sketching a graph. Okay, so I'll show you what I mean by example. So consider a function x squared minus 3 over 2x minus 4. And now it's possible to rearrange this if we notice that x squared minus 3 can be written in terms of the denominator. So if I write half x times the denominator, then that gives me a term x squared. But it also gives me a term minus 2x. So I can cancel that out. And then I can add a 1 to get x squared minus 3. So you just expand brackets. To check this. And it implies, if we substitute in, that fx is half x plus 1 plus 1 over 2x minus 4. Okay. So, of course, the domain of this function is the real numbers with 2 removed, because in that case, the denominator is 0. Okay. So from this form of the function, we can see that firstly, if x is large, either positive large or negative large, then 1 over 2x minus 4 is going to be small. And so I write fx is approximately equal to half x plus 1. So this sign means approximately equal. And then these, they say, are the dominant terms when x is large. Okay, and then secondly, the limit of fx as x approaches 2 is positive infinity. And the limit as x approaches 2 from below is negative infinity. Okay, and this is same as for, say, gx is 1 over 2x minus 4. The terms half x plus 1 do not affect. Limit because it is infinite. So I hope that makes sense intuitively, that if I have a function with an infinite limit and I just add, well, in this case, a term that is approximately 2, if x is close to 2, this term half x plus 1 is approximately 2. That's not going to make a difference to the infinite limit. Okay, and so we could put this information together to sketch the graph. But let me cheat and take a picture from the book. So what do we notice? So fx is approximately half x plus 1 when x is large. So the graph approaches this line, half x plus 1, for large positive x and large negative x. And at 2, x equals 2 is a vertical asymptote. Okay, and another bit of useful information that we could calculate to draw this graph is the y-intercept. So what's that? From the equation, the y-intercept is what is it? So half, 0, yes. We want to put x equals 0 into this equation. Oh, I see, yes. So we put x equals 0 into equation. And we get y is 0 over 2 plus 1 plus 1 over 0 minus 4. It's that minus sign that was confusing me. And the answer then is 3 over 4. And you see that here. Okay, and just to explain this term, oblique. Oblique just means not horizontal or vertical in this case. So in this case, we have a vertical asymptote and also an oblique asymptote. Okay, so before I start a new section, I'm just coming back and looking in the chat. Question about limit laws. If the function is polynomial and infinite, can we still use the limit laws to put the limit inside of the polynomial? I'm not sure I quite understand when you say a polynomial that is infinite. So if I put a number into a polynomial, the result is always finite. Do you mean if I'm trying to take the limit, the limit as x goes to infinity, for instance? Okay, so just a moment, let me think about the best thing to say. Yeah, let me just make this remark. So question. Infinite limits of polynomials. So let's just give an example. Fx is x squared minus x. So in this case, what's the graph? Graph is this. So n1 times oh, thank you, Nat. So I still don't understand, I'm afraid. an1, what are an1 and an2? So the limit of x goes to infinity of fx does not exist. So we can see in this case that as x gets larger, the polynomial itself gets larger and larger. So in particular, so it is not correct to calculate like limit so remember infinity is not a number, just a symbol. Just a symbol. Okay, so I'm not quite sure that's what you meant by your question. I think maybe your question was different, but anyway. Yeah. Okay, let's continue for now. So when x is very large, positively and negative. Yes, thank you, Nat. We can discuss more on WeChat. Yes. So a question about x very large, positively and negative. X over 2 is infinitely large. And we can see that from the graph. So we can see that here. So as x gets very large positively, this y also gets very large, and the limit does not exist as x gets very large. All we're saying is that our function fx gets very close to this line. Okay. So that's what we mean by it's an asymptote. Okay, so continuing. A new section. Tangents. And derivatives. So maybe you've been asking yourself, or other people, why are we calculating all these limits? And so here is the first major application. But we are lucky that we are doing a long calculus course, so we have enough time to learn how to calculate limits, and then we have a lot of skills when we come to use them. So what's the question we want to ask? So question, how to calculate slope of a tangent line. So do I mean if I have a curve like this, and I want to calculate the slope of a tangent line like this, so the answer is to look at what are called secant lines. This is a tangent line here. And the answer is look at secant lines. So that just means lines that join 2 points on the curve. And take a limit. So I'll use diagram from the book because it's drawn there better than I can. So here I'm looking at the tangent at P. So that's the purple line. And the purple line is the tangent at P. And if I then pick another point Q, and draw a second. That's the horizontal grey line. And then I take a limit of those second lines as Q moves towards P. Then you can see that the slope of those lines will approach the slope of the tangent line. And you can see that the same thing would work from the other side. If I take Q as in the right-hand picture, and draw seconds and move Q closer to P, and then the slope of the seconds is going to approach the slope of the tangent line. So for example, let's find the slope of the curve y equals x squared at the point 2,4. So draw this graph. So really not to scale, but if that's 2 and 4, then I want the slope at that point. So I'm going to choose another point Q. This is P, I'll do that later. I'm going to choose another point Q up here and let that have coordinate 2 plus h. So then this will be 4 plus h squared. This is half of h squared. And the second line and this is P and this is Q. This red second line has slope. Remember we said this is the difference in the y coordinate over the difference in the x coordinate, and we can read that off the graph. It's so I made a mistake here. So this is 2 plus h squared. So the difference in the y coordinate is 2 plus h squared minus 2 squared, and in the h coordinate, 2 plus h minus 2. So let's try to simplify that. Well, if I multiply out the 2 plus h squared, I get 2 squared, which is going to cancel, and 2h plus h squared. And then the 2's in the bottom are going to cancel, like that. Oh, so made a simple mistake here. It's 4h. And if we assume that h is positive, which we are in that graph, then we get that result. So here we assume h is positive, same works for h negative. So we say slope at 2, 4 is the limit as h goes to 0 of h plus 4, and of course that's 4. So if we want to draw a tangent, is the line through 2, 4, of slope 4. And so what's that? Well, we put in the coordinates and the slope into the standard equation, and we get 4x minus 4. So we can try and draw that tangent. Its y-intercept is minus 4. So tangent is that. Okay, that came out quite well. So a definition based on this example, the slope of graph y equals fx at this point is, let's call it m. It's the limit as h goes to 0 of the change in the y-coordinate divided by the change in the x-coordinate. So it's between x0 plus h and x0, so it's just h. And this may not exist. We'll see examples where it doesn't exist. Okay, and then the tangent line is y equals fx0 plus the slope times x minus x0. So another example, so we can see this works. If I take y is fx is 1 over x, and I want to find slope at a 1 over a, that's a point on the graph, for any non-zero a, then I can do it using this definition. So m is the limit as h goes to 0. Just putting into the definition of fa plus h minus fa over h. That, if I put in the definition of the function, is, well, it starts out a bit complicated, but we can simplify. So we multiply top and bottom by those two denominators. So we get a minus a plus h over h times the two denominators. Okay, and then I can cancel out the h's. So this is where it's useful. Remember, the limit does not depend on value at h equals 0. We don't have to worry about dividing by 0 in this. And then, well, by the limit laws, that's minus 1 over a squared. So let's try to draw the graph in a few cases. Try a is plus or minus 2. Then m is minus 1 over 2 squared. So that's minus 1 over 4. So what's the equation of the tangent line? For a equals plus 2 is y. So the value is 1 over 2. M is 1 over 4. This is x minus 2. So this, what do I get? I get 1 minus a quarter x. So let's try to draw the graph. Like this. Then I think 1 over x should look something like this. Yeah, maybe that's about right. So at this point, where the value is 1 for x equals 1, and then 2, the value should be a half. But the tangent line has x-intercept 1. Let's try and draw that. Yes. Okay, so that's the tangent line. Okay, and so it's a mirror image here. Okay. So we can use limits to help us just understand graphs, and that provides a lot of good practice in the techniques. But in the real world, we want to use limits to understand rates of change. So, example from before. When I took y is a function of t, 16t squared, okay, let's take a break. Okay, so a question in the chat. In this example, if fx is x squared minus x, why can't we say the limit as x goes to infinity is positive infinity? Because we can see from the graph that as x gets larger and larger, the function gets larger and larger in the positive sense. So there is a way to define this to be true, but I want to be careful about saying anything about it, because we've just defined these two sorts of limits here. So these two sorts of limit here. So x approaches a finite number, gives an infinite limit, and x approaching infinity gives a finite limit. So I don't want to have infinity in both places, because things get a little bit more complicated then. Okay, so I know that's not a very satisfying answer, but yeah, I'm just saying you have to be careful about those sorts of statements and to leave that to a later time. Okay, thank you. Let's continue. So, continuing this example, so the position y, so y can be the distance fallen of some object increasing over time. And remember, the average speed for time in an interval from A to B is the change in y, the change in the position over the change in t. And now if I take t in the interval from 1 to 1 plus h, then this equals this formula we've been using. And if I do the same sort of calculation as earlier in the lecture, I get 16h plus 2 new page. And now we can say that the limit as h goes to 0 is 32. So if you look back in the notes, we predicted this. From calculations. But now we can prove it. Algebraically. And using the precise definition of the limit. Okay. So, So we calculated the slope of graphs at a particular point, and we also showed in certain cases we could calculate the slope at any point. So in that case, we can get something called the derivative function. F prime of f. So that's a function with values given by calculating the slope of the graph. So again, I take the limit as h goes to 0 of the change in the value over the change from x to x plus h, just h. And again, this is if the limit exists. So if limit exists, we say f is differentiable at x, and the value f prime x is the derivative. So this f prime is the derivative function. So we say f prime for this function. And another definition you'll often see, which is just the same, but it can be easier to write in some cases. So f prime x is the limit as another z goes to x of fz minus fx over z minus x. So how do we get this? We note we just write z as x plus h. So then as h approaches 0 in the top definition, z approaches x in the bottom definition. H, of course, is z minus x. So now we can start calculating derivative functions from these definitions. So, example, find derivative of the square root function for positive x. So I let fx be the square root of x, and then using this second definition, f prime x is the limit as z goes to x of fz minus fx over z minus x. So that's the limit z goes to x of root z minus root x over z minus x. And now to calculate this, we have to use the difference of squares formula, but in a bit of a strange way, because z is the square root of z, and x is the square root of x. So the denominator equals that. And that cancels with the numerator. So we just get this. And then by the limit laws, this is 1 over 2 square root of x. So for instance, f prime 4 is 1 over 4. So let's draw a graph. This is not very good. Oh, no. That is this might work. Oh no, that's not. It's not going to work. It's quite a hard one. So okay, maybe something like that. Yeah, maybe this will work. So say this is 4, and then the value will be 2. But this is telling us that the slope is 1 over 4. So if the slope is 1 over 4, then the y-intercept of the tangent line is going to be 1. So try and draw that in. Yeah, okay, so that's not quite right, but if I change the scale a little bit, yeah. Okay, then that's not too bad. Okay, so that's the derivative function, f prime x. There's also lots of other notations for this, which you'll see in the book and in different places. So if I take a function fx and say that's equaling y, then the derivative function f prime x, I can also write this just for short as y prime, and I write it as dy by dx. Okay, so note, this is not a fraction. Just a symbol. So you can't separate the two parts of this fraction. And we also sometimes write df by dx, or we write when we're taking the derivative of something that's longer to write out, often we write it like this. So these are just different notations for the same thing. And there are other notations, but we won't use them immediately, so I'll not write them down. And we say the derivative with respect to x. So sometimes this will be written as WRT. Okay, and other notations, so f prime a, the value at some a, we also sometimes write that as dy by dx. So remember that means another function of x, but restricted to x equals a. And in the same way, we could take this function of x and restrict to x equals a value. Okay, so an example so rate of change again. Showing you how to think of the derivative function when we're using some real world data. So example from the book. So a fun story, in 1988, an airplane was flown from the island Crete in the Mediterranean to a nearby island just by human power. So we have some pictures. This is the flight. So over 100 kilometers, and just by human power. So I have a photo. Oh. shame. So yeah. Anyway, so this airplane was a bit like a bicycle, except with wings. I'll find the photo later. And it was powered by a very fit cyclist. And this graph shows the concentration of his blood sugar as time goes by. So I guess so X So X, I think, is time after launch. Not quite sure about that. But so what and Y is blood sugar of an athlete. So the first graph is a graph of the function y equals fx. So we can see the blood sugar starts high, and then it starts to go down. And at different points, they've calculated the slope. So at A, the graph is flat, so the slope is 0. At B, the slope is -1. At C, the slope is bigger. And then at D, the slope becomes 0 again, the graph is flat, and then starts to go up. So if you imagine calculating all the slope values, then you get a graph of the derivative. So this graph is slope equals f prime x, the derivative. So you can see that corresponding to A, where the slope is 0, there's a point A prime, where the slope is 0, and then the slope goes down to -1, further down to -4/3, and then it comes back up. So we can read off from this graph, from A to C, point A to C, the level of blood sugar is falling, and the rate of fall is increasing. And then from C to D, it's still falling, but the rate of fall is decreasing. And that's because here, in this graph, we can see that the slope is becoming less negative as we go from C to D. And from D onwards, you see it's increasing. Okay, so for this and for all sorts of science, of course, this is extremely useful. So now, in the same way that we had one-sided limits, it's important we define a one-sided derivative. So let's say y. I want to be able to say y equals fx is differentiable on an interval AB if differentiable for all x in AB. So for this, f may not be defined outside this interval AB. And if it's not, then our definition of derivative so far won't work, because we want the limit as h goes to 0 to exist. So h then has to be allowed to be positive or negative. But that's okay. We can take one-sided limits. So we need special definition at the endpoints of the interval. So let me write those down. F prime A, the derivative at A, is given by the limit of this familiar fraction, but now as h goes to 0 from the right. So f a plus h is always going to be defined. A plus h is always going to be in the interval. And the for h negative, we don't see that. So, and in the same way, for b, I want to take the limit as h goes to 0 from the left. Because in that case, I made a mistake, fb plus h. fb plus h. So in that case, b plus h is going to be in the interval a to b. Okay, so I'll give an example of those in a minute. I'm just seeing if there are any questions. No, okay. So these one-sided derivatives are also useful for checking if derivatives exist. So we say the right-hand derivative and the left-hand derivative. So for example, if y is the absolute value function, and then dy by dx, the derivative has values 1 for positive x and -1 for negative x. So we could prove that with our definition, but it's also quite clear from the graph, the slope of the function at those points is that. But what about at x equals 0? So let's first calculate the right-hand derivative. The limit as h goes to 0 from above well, in this, h has to be positive. So the absolute value of 0 plus h is just h, not minus h. And we divide by h, and so we immediately get that the limit is 1. But if we now look at the limit of the same thing as h goes to 0 from the left, now h is negative, so the absolute value of 0 plus h is minus h. And the limit becomes minus 1. So remember that a limit exists if and only if the limit on the left and the right both exist and are equal. So let me just write limit h goes to 0 cannot exist. So function not differentiable at 0. Okay. So another example of when we have problems if y is the square root of x, this is not differentiable at 0 either, but for a different reason. So we draw the graph. So if I look at the tangent line, it's vertical, so we can't define its slope. Its slope would be infinite. So for that reason, if I calculate, I need to take a right-hand derivative because the function is not defined for negative x. But if I take the limit of the usual fraction, this is 1 over square root of h, and that is infinite. Okay, so we say the limit does not exist. And so remember, even though we write limit equals infinity, the limit does not exist. So not differentiable. at x equals 0. Of course, it's differentiable at other points, and we'll see. Okay, so some reasons a derivative may not exist at some point P. So again, we started with this picture of secant lines getting closer and closer to the tangent. But sometimes they can't. Or they do, but that tangent is vertical. So the limit doesn't exist. So let me just, for this, copy in some beautiful pictures from the book. So the first one is a corner. So an example of this is the absolute value function. So it had a corner at 0. And in this case, we can see that if I fix my point P at the corner, and then I take Q minus and Q plus approaching from 2 different sides of the corner, then the tangent lines, but we're not going to get just a single tangent line. So the derivative doesn't exist. Another way to say it is the left-hand derivative and the right-hand derivative are different. So, okay, so question from Ryan, going back, why is this one? So I think, Ryan, you mean this one. So why is that minus h there? So, because in this limit, h is less than 0 because we're taking a limit from the left. So the absolute value of h equals minus h. That's where that minus comes from. I hope that's clear. And you expect this because as I'm coming from the left in this graph, the slope is -1. As I'm coming from the right, the slope is +1. Okay, so here's another example, a cusp. Well, we had a half of this in the example above. So an example of this would be y is the square root of the absolute value of x. So if you think of the graph, it looks a bit like this, but it's upside down. And so as q approaches p from the different sides, we get an infinite slope. Okay. So some other examples from the book. Oh no, not that one, this one. Let's make this a bit smaller. And this a bit bigger. So what we were saying before, you can have a vertical tangent. So the tangent line exists, but its slope is infinite. Or we can just have a discontinuity. So in the case of number 4 on the left, we have q plus going towards p, and that seems to make a nice tangent line. But then Q minus from the other side gives a different direction because there's a jump in the graph. Yeah, and for the same reason in the picture on the right. Okay. So let's continue. Well, a few theorems. I'll try to finish quickly, and then we'll go on to calculating limits. So the first theorem, differentiable implies continuous. So theorem, if f has a derivative at x equals c, then f is continuous at x equals c. Okay, so proof, remember what continuous means. We want to show that the limit of fx as x goes to c is equal to the value of the function at c. So equivalently, if I do a change of variable x to variable h, then I want this. So for this, just put x equals c plus h. And then like before, when h goes to 0, x goes to c. So now, if h is non-zero, then I can write f c plus h in what looks like a crazy way at first. But once we've done this, it'll let us prove the theorem. Okay, so this is just true because if I cancel the denominator on the right, then, it's true if I write it right. Okay, it's FC, FC. So we check by multiplying out. And then we can use the limit laws on this to calculate the limit of the left-hand side as h goes to 0. So that, of course, is equal to the limit of the right-hand side, and fc is just a constant. So I just, well, limit of a constant plus something is the constant plus the limit. And that is a product. Okay, so I'll finish writing this out and I can take a break. Okay, let's continue. So, to explain this proof, we used this equation here, and we took limits as h goes to 0 on both sides. And by the limit laws, this is what we got. But we assumed that f was differentiable. So this fraction has a limit, f prime c. And h also has a limit, that's 0. So as long as this limit exists, f prime c, doesn't matter what it is, in this calculation it gets multiplied by 0, and so the limit of fc plus h as h goes to 0 is fc. And so f is continuous at c. Which is what we wanted to show. Okay, so note this implies that if f is discontinuous, at x equals c, I have to be a bit careful about this. So just think for a moment. Yeah, so I'm going to add in a little bit that the book maybe doesn't explain, or maybe I don't remember from the book. So we're actually assuming f has a derivative at c, and f is defined at c, then f is continuous at c. Okay, so that's just because in the proof we are using implicitly the value fc. I mean, as soon as we start the proof, we're using that value. Okay, so I also want to say now, and f is defined at c. Then f is not differentiable at c. Okay, so let's give an example. The unit step function ux I mean to So I define this to be 1 for x positive and 0 for x negative. So ux, this is discontinuous at x equals 0. Okay, we saw this before, but the reason is that the limit does not exist. Or in other words, the limit from the left equals 0 and the limit from the right equals 1. So they're not equal, so the limit doesn't exist. So by the above, ux not differentiable. At x equals 0. And that fits the pictures we had before. If a function jumps, then we don't expect it to be differential. But this is a proof of it. Okay, so one more bit of theory. This is the intermediate value property. So assume f is differentiable on interval. So let's say on an interval which contains 2 points A and B. Then the derivative f prime takes every value between f prime A and f prime B. Okay, and this is not so important now, but it's important later. So for instance, this function ux cannot be f prime x for any f. Because does not take value half. So by definition, it just takes values 0 and 1. So it cannot be the derivative of any other function. And this will be important later when we're looking for a function that is that gives a function we're interested in as a derivative. Okay. Yes, so a good question from Mu. So by the definition we gave, the function can be differentiable even if it's not defined at C. But actually, I'm not sure. I need to check in the book whether they ask for the function to also be defined. So let me just check that question later. So question. So, so ux is defined just above. Ux is this. Okay, so question. For fx let's see. Do we require fx also defined at c? Okay, so answer, we'll check. Okay. But that won't be important for what we're studying now. It's a good question, but it's not something we need to worry about just now. So now let's start writing down some differentiation rules. So rules for finding derivatives. So let's start easy. If fx equals c is a constant, then the derivative function is just 0. So why is this? Well, we expect this from the graph. If the function is a constant and the slope is 0 everywhere. But this also follows from our definition. But more interestingly, if I take some power of x, so x to the power n, the derivative is this. So, for instance, and we saw how to calculate this before. If I take x squared, the derivative is 2x. But how to prove this more general statement? Well, I'm going to be taking a limit of a fraction where the top is z to the power n minus x to the power n. And I'm just going to use a trick that can be written like this. Sorry, I'm writing this wrong. So let me write it and then explain. Okay, better. So in this big bracket, I've got z to the power n minus 1 on the left and x to the power n minus 1 on the right, and I've got all possible mixtures of powers of z and x in between. And if you multiply this out, you can check that this formula is true. And this is just what we need to calculate the derivative function. Because what is this? It's the limit as z goes to x as zn minus xn over z minus x. And using our equation, this is just the limit of this big bracket. Thing. And, well, by the limit laws, each of these things is going to have limit x to the n minus 1. So in the end, you get n times x to the power n minus 1 from these n terms. Let's check it is n terms. So the power of z here goes from n minus 1 all the way down to 0. So that's n terms in total. Okay. Now, let u and v be functions of x. Now, the function u of x and I apply a constant multiple to it, then it's easy to say what the derivative should be. So constant r. The derivative should just be the constant times that derivative of that function. So for instance, if I have x squared and 2x squared, and I look at the slope at this point, the slope at this point of x squared, then the slope at the same point of 2x squared, of course, is going to be twice. So that's all this, this rule is saying. But all these rules you can prove from the definition. And here's another one. Now let's use both my functions, u and v, and add them. Well, then the derivative is given just by adding the functions. And the same thing if I subtract. So this implies Same result for any number of functions. So for example, we can differentiate polynomials. So if I take y is x cubed, 4 over 3 x squared minus 5x plus 1, and then I want to calculate dy by dx, then the derivative of the power x cubed, remember that formula before, it's n times x to the power n minus 1, so 3x squared. And the derivative of x squared is 2x, and I have a constant multiple 4 over 3. The derivative of x is just 1, and I have a constant multiple minus 5, and the derivative of 1 is 0, because it's a constant itself. So, well, what's this useful? Many things, but the first application is for spotting horizontal tangent lines. So the tangent line is horizontal when the slope is 0, when the derivative is 0. So that means x is a root of the derivative. So the simplest example is y equals x squared. Then dy by dx is 2x, which has root 0. And so we see again that x squared has a horizontal tangent line here. Now we can see the same thing for any polynomial. So x to the 4 minus 2x squared plus 2, and then dy minus dx is 4x cubed minus 4x. And we can factorize this like so and see that the roots are minus 1, 0, and plus 1. So we have horizontal tangents at these points. So, how to draw this graph? Well, this x to the 4 is going to be the dominant term as x gets large. So of course x squared will also be large, but x4 will be even larger, so that will be the dominant term. And then the values of y at these roots. Let's calculate 1 minus 2 plus 2 gives 1. 0 minus 0 plus 2 gives 2. So that. So let's put this together to sketch the graph. Well, first, let me remember x to the 4 is a bit like the graph for x squared, except it starts slower. But then as x gets large, it grows faster. And then I can draw the graph of y against x. So it's going to have these horizontal tangents at the points we've calculated. So at x is minus 1 and plus 1, where the value of y is 1 in both places. And then at y is 2. So putting all this together, we get that the graph is like this. Okay, not great. Yeah, not great, but good enough. Okay. So let me pause there and see if there are any questions. So I see Ben Lee has been kicked out of the Zoom group. Okay. Ah, and now he's back in. Okay. So if there's no questions there, let's continue. So we differentiated powers, x to the 4, x squared, and we differentiated sums, and that let us differentiate polynomials. But to differentiate products is a little bit more difficult. So, well, let's just first remember, so note, could also write yeah, so we introduced this notation, but we didn't use it yet, that y prime is 4x cubed minus 4x. So that just means the same thing as dy by dx. Okay. And so that helps us to write the rule for the derivative of a product. So I still have these functions, u and v, functions of x. And if I want to calculate the derivative of a product, there's a formula for it, but it's more complicated than for a sum, but we'll see why it has to be like this in a moment. So you take your two functions, u and v, you differentiate one, and then you multiply it by v, and then you differentiate v and you multiply it by u. So that's the formula. And this is where this prime notation starts to become useful, because in that notation you can just write like this. So things get quicker. But note, the derivative of u times v is not equal to the product of the derivatives. Okay, so some examples. Well, d by dx of x squared, we already know, but we can use this to see it again. So the formula gives and that just gives 2x because the derivative of x with respect to x is just 1. Okay. So remember that dx by dx is not a fraction, but well, if you think of it as a fraction for at this moment, it helps you remember dx by dx equals 1. So another example, if I want to calculate the derivative dy by dx for y is x squared plus 1 times x squared plus 3. I can do this in two ways. So the first is use the product rule for differentiation. So dy by dx is the derivative of the first thing, so that's 2x, times x squared plus 3, plus x squared plus 1 times the derivative of the second thing. And then we can multiply that out Mm-hmm. 2x. Oh, I think I made a mistake copying from the book, actually. Let me see. So I think one of these should be x to the 3. So if anyone wants to tell me why I've made a mistake, then they can. Nice. In the meantime, I'm just checking this in the book. I see. So it's this 3. Yeah. There's 3 here. Okay, so now we can go through and correct. Okay. Right. Yep. So now I want 3x to the 4 and 3x squared. Okay. And then I get 5x to the 4 plus 3x squared plus 6x. Great, that's what I was expecting. But we can also get this by multiplying out. So y, if I multiply out, is x to the 5 plus x cubed plus 3x squared plus 3. And that implies dy by dx is 5x4 plus 3x squared plus 6x, just like we calculated before. So both methods agree. And this wouldn't work if at this point I had written just these derivatives. So just the derivative of one thing and the derivative of the other thing. That's right. So there's the derivative. And this, the derivative, this, and this. Okay, so the point is, to calculate dy by dx, I have to take the derivatives of the 2 parts, but I also need extra stuff, which is written in this line. So that's the product rule. Okay. Do we need to memorize the proof of differentiation rule? I'm not actually giving the proofs of the differentiation rules in the lecture. So it's good to study these things. That's all I'll say. So continuing, quotient so if I have a quotient of functions, u of v then how to calculate the derivative of that. So I'm just giving the formula, and we can give some examples. So we use the derivatives of u and v, and we combine them with v and u itself. But notice we have a negative here. Negative. Which is the opposite of in the product rule. And we have this v squared on the bottom. Can also write in this other notation u over v prime is vu prime minus uv prime over v squared. So maybe it's easier to remember like that. And so let's give some example. If y is t squared minus 1 over t squared plus 1, then y prime, the derivative, well, we take v from the bottom and multiply it by u prime, which is 2t. And then we take u from the top and multiply it by v prime, which is 2t. And then we put a square on the bottom. So if I multiply that out, I get on the top 2t cubed and minus 2t cubed, and they cancel. And I get two 2t's, and they don't cancel, they give a 4t. Okay, so that's an example. So an application of this rule is to differentiate negative powers. So let me just finish the statement. So for integers n less than 0, the derivative of x to the power n is given by the same formula as for positive powers. But we need that x is non-zero. So we'll prove this next time. Okay, see you on Thursday.